Hello everyone, this is Rahman Muhammad Abdul, and today I'll be presenting the R-star tree, an efficient and robust access method for points and rectangles. This research was conducted by Norbert Beckmann, Hans-Peter Bernhard Seeger. The R-star tree is an evolution of the R tree, a fundamental structure for indexing multidimensional spatial data such as points and rectangles. Our discussion will cover its motivation, design improvements, and how it addresses the limitations of previous structures. Here is a quick look at the topics I'll be covering. We will start by establishing a clear understanding of the basic terminology and definitions. Then we will move on to the R tree and its structural components. After that, we will look into the variants that were developed to improve R tree performance, followed by the problems those variants faced. This sets the stage for introducing the R star tree, where we will delve into its key innovations such as its split strategy and reinsertion mechanism. Finally, we will look at experimental results, applications, and conclude with the overall benefits of the R-star tree. Before diving into the structure, it's essential to understand some fundamental terms. The margin of a rectangle is the sum of the lengths of its edges, which plays a key role in minimizing spatial spread. PAM or point access method refers to data structures and algorithms designed for efficiently locating points in multidimensional space, a principle that underlies the R-tree family. Data space represents the full dimensional area in which our data lives, and node capacity, typically defined as m and m, sets the lower and upper limits for entries in a node. These parameters directly affect how deep or wide the tree becomes. The R tree is a balanced tree structure developed for indexing multidimensional objects commonly used for spatial data like rectangles, lines, and points. Its strength lies in enabling fast lookups for queries involving spatial relationships, such as intersection, containment, and proximity. On the other hand, the R-star tree is an enhancement of the R tree. It retains the hierarchical design but improves performance through more intelligent insertion and split strategies. It emphasizes reducing node overlap, compacting node shapes, and delaying splits through reinsertion, all aimed at improving search performance and efficiency. Notably, the R in both terms represents rectangles or regions. Spatial data includes any geometric representation like points, lines, and rectangles. To manage such data efficiently, we rely on spatial access methods or SAMs. These methods simplify complex shapes by wrapping them in minimum bounding rectangles or MBRs. This way, even irregular shapes can be stored and queried efficiently. The R-tree, introduced in the 1980s, became the most widely used SAM for rectangles because of its dynamic structure and practical performance. Today, many applications from ride-sharing apps to GIS platforms and even drone navigation systems rely on spatial queries. For instance, asking which buildings are near this location involves spatial indexing often handled by structures like the R-tree. The R-tree builds upon the idea of B plus minus trees, but it adapts this concept for spatial domains. Instead of keys, the R-tree stores rectangles. Each internal node contains references to its children along with the MBRs that encloses them. Insertions and deletions are dynamic and recursive, updating parent nodes accordingly. The tree is kept balanced by maintaining node capacities defined by a minimum of small m entries and a maximum of capital M. If a node overflows beyond capital M, it triggers a split. What makes the R tree powerful is that it allows overlapping rectangles across nodes, a necessary trait for representing complex spatial layouts, though it introduces performance trade-offs we will explore shortly. To understand how data is organized, let's look at the two types of nodes in an R tree: internal nodes store child pointers and bounding rectangles, essentially acting as decision points in the tree. Leaf nodes store the actual data entries, usually object identifiers and their associated bounding rectangles. One key property is that all leaf nodes are at the same depth, ensuring balanced query time across the tree. Each node must maintain between small m and capital M entries to ensure space efficiency. The effectiveness of an archery largely depends on how these MBRs are shaped and how much they overlap, which directly affects query performance. Over time, several archery variants were introduced to improve insertion, quality, and query speed. The original archery by Gutmann uses an area-based strategy to determine where to insert or split nodes. The linear archery simplifies this with a faster but less precise method that picks seeds based on extreme values. It's fast but often results in poorly clustered data. The quadratic archery, also by Gutmann, uses a more refined selection of seeds that aims to minimize wasted space. It offers better query performance but has higher insertion costs. Then we have Green's archery, which focuses on axis-aligned splits. It works well for evenly distributed data but struggles with irregular clusters. None of these variants effectively address all core issues, especially overlap and poor shape. Optimizing an R tree involves balancing four key criteria. First, we try to minimize the area of each bounding rectangle, ensuring compactness. Second, we aim to reduce overlap between rectangles. The less they overlap, the fewer false paths are explored during queries. Third, minimizing the margin or perimeter helps generate square-like rectangles which are more efficient in storage. Finally, maximizing storage utilization keeps the tree shallow and reduces the number of disk accesses. However, focusing on only one criteria, such as area, can negatively impact the others. That's where the R star tree offers a more balanced approach. Despite the efforts of R tree variants, serious problems persist. Diagrams in the original paper illustrate these clearly. For example, in Figure 1a, we see a well-balanced and non-overlapping split, the ideal scenario. But Figure 1b shows uneven node distribution where one side gets more rectangles leading to poor storage usage. In Figure 1c, we see heavy overlap, which is detrimental for query speed. Figure 1d presents rectangles that are long and narrow, poor in shape and difficult to cluster. Even Green's method, as shown in Figure 2c, can result in overlapping splits. These issues highlight why heuristic approaches alone aren't enough, paving the way for a smarter solution, the R-star tree. The R-star tree was designed specifically to overcome the flaws of existing variants. Its goals include reducing the number of nodes accessed during queries, improving how data is spatially clustered, and being adaptable across different data distributions. Unlike prior methods that focused mostly on area, R-star tree takes a combined approach by considering area, overlap, and margin during its optimization steps. For example, you can see the fig. It shows Green's method selecting a poor axis, which R-star tree corrects by evaluating splits along both axes. These innovations make the R-star tree more robust and reliable across real-world applications. One major improvement in R-star tree is its choose subtree algorithm. Instead of simply minimizing area enlargement, it considers how much overlap would be introduced by inserting a new rectangle into a given node. Another breakthrough is forced reinsertion, a technique where instead of immediately splitting an overflowing node, The algorithm removes a few strategically chosen entries and reinserts them elsewhere in the tree. This rebalancing improves the overall structure. Additionally, R-star tree evaluates multiple access and partitionings during splits. These techniques require slightly more computation during insertion but lead to significant improvements in query performance. Splitting an R-star tree is a multi-step process. First, it evaluates all possible splits along both the x and y axis. For each candidate, it calculates the total margin, area, and overlap. The axis with the smallest margin sum is selected, and within that, the grouping with the least overlap is chosen. This two-phase evaluation ensures the resulting rectangles are more compact and better clustered. In Figure 2b, for example, traditional methods fail to split clustered rectangles properly, resulting in overlap. R-star tree's smarter evaluation avoids this, leading to more efficient spatial grouping and faster query times. One of the most unique aspects of the R-star tree is forced reinsertion. When a node overflows, instead of splitting immediately, the algorithm removes about 30% of the entries that are farthest from the node's center. These are then reinserted into the tree, possibly at better locations. This process delays or even avoids splits altogether and improves how well entries are spatially grouped. It also helps the tree self-optimize over time. While it adds some cost to insertions, the performance benefits, especially in query handling, far outweigh this overhead. To evaluate the performance of the R-star tree, the authors conducted comprehensive experiments using various datasets, each simulating different spatial distributions. These included uniform random distributions, clustered datasets, and real-world data extracted from applications like digital elevation models and map-based datasets. The dataset consisted The dataset consisted of over 1 lakh rectangles in 2 dimensions, simulating a fairly large workload that mirrors practical usage in geographic or CAD applications. The evaluation covered multiple query types, including intersection queries, where we ask which object overlaps with a given region; point queries, to determine which object contains a specific point; enclosure queries, to find objects fully contained within a given area; and spatial joins, which are more complex, involving comparison of object pairs across two datasets to detect spatial relationships. What's important here is that these are the core operations most spatial databases must handle efficiently. The performance in these categories reflects how well an indexing structure performs in the real world. This diversity in testing ensured that the R-star tree wasn't just optimized for a niche scenario, but is applicable to general purpose spatial indexing tasks. You can expand this view further with examples. Imagine a city planning tool where you need to find all parks that intersect a flood zone. That's an intersection query, or finding which parcel of land contains a point where a water leak is reported. That's a point query. Now let's look at the performance results. The R-star tree outperformed all the other R-tree variants in nearly every category. Specifically for intersection queries, which are among the most demanding, the R-star tree achieved up to 4 times faster response times compared to the linear R tree. This improvement is due to the reduced overlap and better node clustering achieved by the reinsertion and multi-axis split strategies. What's equally impressive is that despite introducing more complexity during insertion, such as sorting and overlap checks, the R-star tree still had lower overall insertion cost than the alternatives. That might seem counterintuitive, but the delayed or avoided node splits and better tree structure mean fewer cascading splits and less rebalancing in the long run. Also worth nothing in Also worth is storage utilization. The percentage of node capacity that's actually used. A high utilization means the tree stays shallow and efficient. The R-star tree had the best number here too, which translates to fewer disks, I/O operations, a major performance factor for database engines. Another important metric is robustness. The R-star tree performed consistently across all data set types, uniform, clustered, or skewed. This consistency means that developers can rely on it regardless of data characteristics, which is crucial in dynamic real-world applications. You can also engage in working on a geospatial app that handles both downtown grids and rural layouts. The R-star tree adjusts just fine. While the R-star tree was originally designed for spatial objects like rectangles or polygons, its versatility extends further. When dealing with point data, we can treat each point as a degenerate rectangle, that is, a rectangle where width and height are zero. The R-star tree not only handles this scenario well, but actually outperforms specialized methods like the two-level grid file, which was previously a popular approach for point indexing. This result is significant because it demonstrates that R-star tree isn't a one-trick solution, it's adaptable and efficient for both range-based spatial queries and exact point queries. That makes it a strong candidate for systems where both types of data coexist, like traffic monitoring systems where points represent vehicles and zones are stored as rectangles. In conclusion, the R-star tree offers significant improvements over earlier R-tree variants in terms of query performance, storage efficiency, and adaptability. Its smarter split strategy, which considers area, margin, and overlap, combined with the novel forced reinsertion technique, leads to more compact and better balanced trees. These design decisions directly translate to faster queries and better scalability. The slightly higher the slightly higher implementation complexity is well justified by the performance gains. In fact, many modern spatial systems and databases such as Postgres, Oracle Spatial, and Boost Geometry now implement the R-star tree as the default spatial indexing structure. If you come to real-world applications of the R-star tree, it includes Geographic Information Systems (GIS), where spatial queries are central, CAD tools, which use it to manage drawings and layers, game engines for collision detection and spatial partitioning, environmental monitoring to detect overlap of hazards with protected zones. As spatial data becomes increasingly prevalent in smart cities, autonomous systems, and even augmented reality structures, like the R-star tree, become indispensable. Future extensions may include support for complex polynomial data, 3D spatial data, and integration with machine learning based query optimizers.